Okay. So by now we know that X transpose Y, if it is equal to 0, the vector X and Y are said to be orthogonal. So the vectors the vectors X and Y are orthogonal if X transpose Y is equal to 0. This is what we know. But not all the time. This concept of orthogonality is quite important. I mean, when you go for, we'll see in subsequent classes, like we'll see in subsequent classes how they are very much useful in our day-to-day operations and different operations. But then one thing for sure, that not all the vectors are orthogonal. So the life doesn't stop with that, right? When you don't have an orthogonal vectors, your life doesn't stop. So you need to carry on. So this is what the precursor to the next class. And let us consider um, let us consider the vector A. Let us consider another vector B. And clearly A and B are not perpendicular. They subtend an angle theta with each other. And what we want to find here, the not the exactly the concept of orthogonality, but we want to make something similar to this, how they could be orthogonal with each other. One of the way to make orthogonal with each other is find the line that is perpendicular from B to A. Why it is important? Perpendicular to B to A. So let us say this is the vector P. So the line connecting B to P is perpendicular to A. So let me write it. The line connecting B to P is perpendicular to A. And this is what we call as projection of B onto the line through A. Projection of B onto the line through A. So why it is so important? So this red line, why it is so important? Because if I draw this red line, something like this, then you will realize why it is so important. Any idea why? What is the relationship between this? Now look at this green line and this red line. This green vector A and this projection vector. This is actually the projection vector. But I am drawing a parallel projection vector to onto this. Now this A and this projection vector are orthogonal. So even though A and B are not orthogonal, but the concept of orthogonality we can introduce through this. And this is what is important is. Okay. Okay. So let us proceed, and let me what happened to this? Okay. Sometimes they misbehave actually. Okay. So let me take this one. This is my x-axis. This is my y-axis. We are considering this one on a two-dimensional plane, which you can extend it to any dimension as you like. This is my origin. And let us say this is the vector A. This is the vector B. Okay. And this is the vector this plus this is equal to this. So A minus B. Okay. So here I have the length A. Here I have the length B. Here I have the length A minus B. And let us assume that it subtends an angle alpha. It subtends an angle beta. And this is equal to theta. Okay. Clearly theta is equal to beta minus alpha. Theta equal to beta minus alpha. Okay. Now let me draw two perpendicular lines. One from here and another from here. Fine. So let me name it as Q, and let me name it as R. So now we have two triangles. Triangle 1 is O A Q, and another triangle O B R. The other two triangles we have. Fine. Okay, let me also write this one. The coordinate of A, it's a two-dimensional plane. A1, A2, and B is equal to B1, B2. X value is A1, Y value is A2. B1, B2 respectively. So from the triangle OAQ, can I write like this? Sine alpha is equal to A2 by A, and cos alpha is equal to A1 by A. Similarly, from the triangle OBR, sine beta is equal to B2 by B, and cos beta is equal to B1 by B. That's how I can write. And obviously, cos theta is equal to cos beta minus alpha, which is nothing but cos, what is the formula? Beta cos alpha plus sine beta sine alpha. That's how it becomes. Cos beta cos alpha sine beta sine alpha. Yeah, that's right. So yeah, I can write it as cos beta cos alpha, cos beta cos alpha is nothing but A1 B1 by A norm B norm, and sine alpha sine beta is A2 B2 by A norm B norm. So A norm B norm I can take common, and this becomes A1 B1 plus A2 B2. What is A1 B1 plus A2 B2? Does it look familiar to you? A1 A2 is a vector, B1 B2 is another vector. A1 B1 plus A2 B2. This is nothing but vector A transpose B divided by length of A vector, length of B vector. And the same thing can also be obtained from the laws of cosines. From the law of cosine, this is what also you can obtain. A minus B square, length square, is equal to this A minus B. A square plus B square minus 2 cos theta. What is A minus B square? Can I write it like this? Can I write it like this? A transpose A minus 2 times A transpose B plus B transpose B is equal to A transpose A plus B transpose B minus 2 times cos theta, and it results in the same thing. No change. In fact, I should not write in that way. Let me write it in this way. Cos theta it is the same thing, right? Now, where we started actually, we started from here. Our objective is to find this red line, the projection of B onto the line through A. That is what our objective is. Okay. So, what is P? What is P? Can I write P is equal to the vector P is equal to some scaled version of A? I can very well write, right? The vector P is a scaled version of vector A. So let me write like this. Vector P is equal to some scaled version. Let us say the scale is x cap, scaled version of A. So go back to this diagram. Let us say this is the vector C is equal to um, it's like P plus C is equal to B. So C is equal to B minus P. So B minus P and A are perpendicular. B minus C and A are perpendicular. So I can very well write C is perpendicular to A, or so to say B minus P is perpendicular to A. Or in this way, I can write A transpose B minus P is equal to 0. That is what I can write. Or A transpose B minus x cap A is equal to 0. This implies that A transpose B minus x cap. X cap is a scalar quantity, right? I can take left, right, wherever I want. So so this implies that x cap is equal to A transpose B divided by A transpose A. A transpose B is a column vector, A transpose is a row vector. Row vector times column vector, that becomes a scalar quantity, and denominator is also a scalar quantity. So this becomes a scalar quantity. So what is P? P is equal to x cap A, which is nothing but the scalar quantity A transpose B upon A transpose A times the vector A. So this is what is our outcome is. Fine. Now, um, just let us see how it works actually. If at all you are asked to project B, let us say 4, 5, 6 onto A 1, 2, 3. So what will be the answer? First of all, find out what is X cap. X cap is A transpose B. So you have 1, 2, 3. B is 4, 5, 6 divided by 1, 2, 3. 1, 2, 3. So what is the answer? 32, right? Is the denominator or numerator?
32 by 15.
32 by 15.
14.
14.
14, sir. 14.
14, sir.
So that will come around 2.29. 2.29. And what is P? Is equal to 2.29 times 1, 2, 3. 2.29 2.29 into 2, 4.58, 2.29
6.87.
into 3, 6.87. Okay, but then in not only in mathematics, in every walk of life, we actually take care of aesthetics, right? Little bit of aesthetics is also required. Without aesthetics, things look very dull. And not all aesthetics should be of crap kind of things. Rather, they should have some amount of reasoning, isn't it? So people started working on that. So what is that aesthetics? So here comes the definition of projection matrix. Well, let me rewrite this P is equal to X cap A, and this is equal to A transpose B upon A transpose A. Let me do little bit of alteration. Let me bring this vector A on the front side. That won't change the things actually. A transpose upon A transpose A times V. Or it's something like writing uppercase P V. Now, why at all people started doing like this? It's like you have a line A, you have another line B, projection of B onto A. Now, let me draw few variations. This is B, this is A, this is B, this is A. Doesn't matter if the B is same, and irrespective of the magnitude of A, the A vector, it should project onto the same, the projection should be the same, right? So it is like the projection matrix is made up of the vector A. The projection matrix is made up of the vector A because you are projecting a vector B onto a vector A. So that onto part, the vector A should be unique, should be invariant to whatever B you have. So this B or this B or this B, this vector A should be invariant. I'm sorry, not the vector A. The projection matrix onto A should be invariant. And this is what the projection matrix is. P is equal to A transpose A transpose A. A transpose A, the denominator is a scalar quantity. A transpose, it is column times row. This gives you a matrix. Say for example, let us say A is equal to 1, 1, 1. This A is the line passing through 1, 1, 1. So what is P? 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. What is that? The denominator becomes 3, 1 upon 3. This is 1 upon 3, the denominator part. And the numerator is nothing but 1, 1, 1, 1, 1, 1, 1, 1, 1. So this is what your projection matrix is. Either you write like this or you write like this. What is the rank of P?
One.
That's 1.
1.
Right from the first class, if you recall, we are always interested in rank 1 matrix. That solves actually lots of problems. We will converge in couple of few classes down the line. We will converge with this rank 1. Why at all these rank 1 businesses there. So the column space of this particular matrix P is the line passing through 1 upon 3, 1 upon 3, 1 upon 3 or 1, 1, 1. The column space. Rank is equal to 1, column space is 1. Column space is the line passing through A equal to 1, 1, 1. And not only that, every column of this matrix is multiple of A. There is also a fact. Every column of P is a multiple of A. And that is what exactly we have written earlier. PB is equal to X cap A. And PV equal to X cap A. And I started with this actually. Yeah, this diagram. What is this then? This is nothing but the vector B the vector B projected onto P equal to 0. The vector B projected onto P equal to 0. And this is what it gives and then what you have is this vector transpose this vector, or this vector A vector transpose this vector, that gives you 0. That is what the orthogonal is. Yeah. So that is where we started, and now we are with this. Yeah, one more property, P is symmetric. We forget to write that. P is symmetric. So that's it. So the takeaway from this class is lowercase p is equal to uppercase P B. That is what the takeaway. And with this, we'll start the next class. We'll stop here. By the way, you also find out what is P square would be. This I leave it to you. What is P square? What properties it has got? One more thing. What happens if, yeah, that is what I have written here, drawn here actually. Irrespective of the value of A, irrespective of the value of A, this A, the projection of B onto A is constant. So that also need to be verified. So I leave that also to you. Find out the behavior of A on the projection of B onto A. That also I leave it to you. So what happens if A is doubled? Let us see. What happens if A is doubled? What happens if the sign is changed? So like that. Okay. So that's all. That's all for today. Thank you.